In the given figure, block 1 is 1/4 of length L of block 2 of mass also 1/4. That is, we have block 2 having mass 4m and length L, and a block 1 having mass m and length L by 4. There is no friction between block 2 and surface on which it rests. So there is no friction between 4m and the floor. Coefficient of friction is mu k between 1 and 2. Between 1 and 2, the coefficient of friction is mu k. Now, we need to find the distance block 2 moves when only half of the block 1 is still on block 2. So, we need to find the distance covered by this 4m mass when only half of the block 1 is on block 2. Rest it has come out. That means finally its position will be something like this, and there L by 8 distance of the block will be out of 2. Now block 1 and block 3 have same masses. 1 and 3 both has mass m. So if we draw now their free body diagram, let us consider mg to be the force acting on m third block in downward direction. Let T be the tension. T be the tension here also. As this block is being pulled, friction will be acting in backward direction on this particular block. This is the frictional force, and on block 2 frictional force will be acting in forward direction. Due to these forces, let us assume that this third block is moving downward with acceleration a1. As third is moving downward with acceleration a1, 1 will also be moving with respect to a1. And as frictional force is acting in forward direction on 4m, so it will also be moving forward. Let its acceleration be a2. So 2 is moving with a2, 1 is moving with a1, and relative acceleration of m, a relative, will be equal to a1 minus a2, with which 1 is moving with respect to 2. Now from the free body diagram, if we write the equations, we can write mg minus t is equal to ma1. Here from we can write t minus f is equal to ma1. So here from we can write mg minus f is equal to 2ma1. As the mass is moving, block 1 is moving with respect to 2, friction is maximum, it is limiting friction, and it is mu k mg. So we can write mg minus mu k mg is equal to 2ma1, or a1 is equal to g into 1 minus mu k by 2. This is the acceleration of the block 1. Now for acceleration of block 2, we can write f is equal to 4ma2, or mu k mg is equal to 4ma2, or a2 is equal to mu kg by 4. So the relative acceleration of block 1 with respect to 2, a relative, is equal to g by 2 1 minus mu k minus mu kg by 4. So if I take g by 4 to be common, then it is 2 minus 2 mu k minus mu k, or it is g by 4 into 2 minus 3 mu k. This is the relative acceleration of block 1 with respect to block 2. Now, with respect to block 2, the block 1 moves the distance of L minus L by 8. So, distance travelled by 1, S1 is equal to L minus L by 8, let the time taken is t, so this is equal to half A relative into t square. So here from we can write 7L by 8 is equal to G by 8 into 2 minus 3 mu k into t square. So here from we can write t square to be equal to 7L by G into 2 minus 3 mu k. And as the second block is moving with acceleration a2 in the same duration, so distance travelled by 2 in the same duration, h2 is equal to half a2 into t square, that is equal to half a2 we have already obtained, mu kg by 4 into t square, that is 7L by G into 2 minus 3 mu k. So here from we obtain H2 to be equal to 7 mu k L upon 8 into 2 minus 3 mu k. This is the distance travelled by the second block in the given duration.